The refraction of light through lenses alters the characteristics of images. We can employ this property of lenses in a variety of ways. In this lesson, you will learn about lenses and their uses. At the end of this lesson, you will be able to define a lens, list the types of lenses, analyze the refraction of light rays through a convex lens, analyze the refraction of light rays through a concave lens, apply the lens formula and sign convention to find the image distance, and to find magnification. Spectacles use lenses to form clear and sharp images. A lens is defined as a piece of transparent optical material with one or two curved surfaces to refract light rays. A lens may converge or diverge light rays to form an image. Reading glasses, binoculars, and optical instruments, such as telescopes, use lenses to enhance images of objects. Based on their shapes, lenses can be of 5 types. A biconvex lens is one with a surface that is bulged outwards on both the sides. It is generally referred to as a convex lens. Another type of a lens is a biconcave lens that has 2 inward bent surfaces. It is generally referred to as a concave lens. A plano-convex lens has a convex surface on one side and a plane surface on the other. A plano-concave lens is the one that has a concave surface on one side and a plane surface on the other. A concavo-convex lens has a concave surface on one side and a convex surface on the other. Convex and concave lenses are important as they are more commonly used than the other types of lenses. We will focus on these 2 types of lenses in our study. In your study of lenses, both convex and concave, you will use some general terms to identify the location of images. Optic center is a point on the axis of a lens such that any light ray passing through this point emerges without refraction. It is also known as the pole of the lens. As shown in the figure, O is called the optic center of the lens. Principal focus. Principal focus is a point on the axis of a lens. This is the point where a beam of light parallel to the principal axis, after getting refracted, meets in a convex lens or appears to meet when produced backwards in a concave lens. Principal foci occur on both sides of lenses. Principal focus is also known as the focal point. In the figure here, F1 and F2 are the 2 principal foci. In a convex lens, if an incident ray passes through a focus and its emergent ray passes parallel to the principal axis, then that focus is called the first principal focus. If an incident ray passes parallel to the principal axis and its emergent ray converges at a focus, then that focus is called the second principal focus. In a concave lens, if an incident ray is directed towards a focus and its emergent ray passes parallel to the principal axis, then that focus is called the first principal focus. If an incident ray passes parallel to the principal axis and its emergent ray appears to diverge from a focus, then that focus is called the second principal focus. The distance between the optic center and the focal point is called the focal length. Here the focal length has been represented as OF1 and OF2. A lens in which both the surfaces are convex is known as a convex lens. Light rays incident on a convex lens get converged at its focus. This is why a convex lens is also called a converging lens. Children often use them to make paper burn by making sound rays converge on a point on the paper. Convex lenses are used as magnifying glasses by palmists to study palms. They're also used by fingerprint experts for magnifying and studying fingerprints. Now let's analyze the light rays propagating through a convex lens. When an incident ray is parallel to the principal axis, the emergent ray passes through the focus. When an incident ray passes through the optic center, it propagates without any deviation. When an incident ray passes through the focus of a convex lens, the emergent ray passes parallel to the principal axis. Thus, we can predict the positions and the characteristics of the images formed using convex lenses, based on how a light ray incidents on the lens. For each position of the object, consider two light rays emanating from a point on the object. When an object is placed at infinity, the image is formed at f2 and is real, inverted and highly diminished. When the object is placed beyond 2f1, the image is formed between f2 and 2f2 and is real, inverted and diminished. When the object is placed at 2f1, the image is formed at 2f2 and is real, inverted and of the same size as the object. When the object is placed between 2f1 and f1, the image is formed beyond 2f2 and is real, inverted and magnified. When the object is placed at f1, the image is formed at infinity and is real, inverted and highly magnified. When the object is placed between f1 and O, the image is formed on the same side of the lens as the object. The image is virtual, erect and magnified. A lens in which both the surfaces are concave is known as a concave lens. Light rays incident on a concave lens get diverged away from the principal axis of the lens. An image formed by a concave lens is always diminished due to the divergence of rays. This is why concave lenses are widely used to correct eye defects such as myopia. Thus, a concave lens is also known as a diverging, reducing, negative, myopic or minus lens. Now let's analyze the light rays propagating through a concave lens. When an incident ray is parallel to the principal axis, the emergent ray appears to pass through the focus. When an incident ray passes through the optic center, it propagates without any deviation. When an incident ray is directed towards the focus of a concave lens, the emergent ray passes parallel to its principal axis. Thus, we can predict the positions and the characteristics of images formed using concave lenses, based on how a light ray incidents on the lens. For each position of an object, consider two light rays emanating from a point on the object. When the object is placed at infinity, the image is formed as a point at f1 and is virtual, erect and highly diminished. When the object is placed beyond 2f1, the image is formed between f1 and O and is virtual, erect and diminished. When the object is placed between O and f1, the image is formed between f1 and O and is virtual, erect and diminished. The lens formula defines the relationship between the focal length of the lens f, the distance of the object from the optic center U, and the distance of the image from the optic center V. 1 divided by f is equal to 1 divided by V minus 1 divided by U. To denote the distance and the nature of the image formed by a lens relative to the object, some conventions have been defined. All the distances are to be measured from the optic center of the lens. The distances measured in the direction of the incident light are taken as positive. The distances measured in the direction opposite to that of the incident light are taken as negative. You can determine the size of the image of an object if you know the magnification of a lens. Magnification, denoted by small letter m, is the ratio of image size to object size. It is also measured as the ratio of image distance to object distance. Thus, magnification is unity when the size of the image is equal to the size of the object. Magnification is greater than 1 when the size of the image is greater than that of the object. Magnification is less than 1 when the size of the image is less than that of the object.